Okay, here we go. So 10.9, real gases, deviations from ideal behavior. This equation here is just Pivnert rearranged to solve for n, which is number of moles. They give us some other information here. For 1 mole of an ideal gas, PV over RT equals 1 for all pressures, which makes sense because if that's number of moles, if it's 1 mole, then that should equal 1. In a real gas, PV over RT varies from 1 significantly. The higher the pressure, the more the deviation from ideal behavior. So everything that we've been doing so far in terms of equations and all that kind of stuff is based on what they would call ideal behavior for a gas under certain conditions. In real life, things vary and it changes how the gases act. So higher pressure or lower temp, so in other words, the higher the pressure or the lower the temperature, the more the gases do not follow ideal behavior. Okay. So assumptions in the kinetic molecular theory show where ideal gas behavior breaks down. The molecules of a gas do have a finite volume. In other words, if you, well, no, it's like if you took a tank of oxygen out to outer space and you just released it, the molecules would expand, but they wouldn't expand to fill everything. Yeah, well, it wouldn't hold a volume, but it wouldn't expand out to fill the whole of the space area or whatever. Like, there's things that limit it, gravity, stuff like that as well. Like, we know that our atmosphere on Earth is essentially made up of gas molecules that are held close to Earth by Earth's gravity.
I was going to say, does air not fill out the atmosphere?
No, it does. However, there are different levels. Like, so you guys know about the ozone layer, right? Ozone is a gas. But because of different gas properties and gravity and densities and stuff, like O3, ozone actually around the Earth is at a certain layer. So just like, you know how like liquids will have different densities and some will sit on top of the others or they won't mix or whatever, gases actually can do that too.
Oh, what?
Yeah.
Red Bulls?
You know, depending on the makeup or the mixture of the gases, they could actually have, you could have different layers based on the gas as well. Actually, a good example of that is carbon dioxide, you know, dry ice, when it turns into gas, carbon dioxide. If you have too much of it, or if you got a lot of it, carbon dioxide in general is heavier, so it'll sink to the bottom of the floor. And if you get too much buildup, it can, like, people can die if you get too much of it built up, because it essentially it all sits along the bottom and then it can build up and then.
Like when you start your car in a garage or something?
That would be another example. That would be carbon monoxide. But but in that case, it's like replacing oxygen. But the effect would be similar in terms of it if you get too much of it built up. Now, carbon monoxide is still dangerous, but that actually is lighter, so it mixes a little more easily. Okay, so as the pressure on the gas increases, the molecules are forced closer together. As the molecules get closer together, there's less free space. So the smaller the container, the more total space the gas molecules occupy. And the closer the molecules get together, the more intermolecular forces start to affect them. So we know that like a gas can turn into a liquid, and basically what happens is the molecules get a lot closer together. Well, in a liquid, intermolecular forces affect the molecules. So it makes sense that when gas particles, even if it's still as gas particles get closer together, intermolecular forces start to have an effect, which is what I've highlighted here. The smaller the distance between the gas molecules, the more likely that attractive forces, intermolecular forces, will develop between the molecules. Therefore, the closer together they get, the less the gas resembles an ideal gas. Okay. All right. So, what does this look like? Well, this is shown in something called the van der Waals equation. In the van der Waals equation, they have corrections for ideal gas behavior or non-ideal gas behavior. The volume of molecules. So in this, the V minus NB, the volume here would represent the ideal, and then the NB is the correction, and then this V thing is the real, would be the real volume after it's corrected.
So that would be what you get.
This would be what actually is the volume when you correct for non-ideal gas behavior. Is what that would be for that. So
is that part of the equation?
Yeah, sort of like this is you're substituting in. So in other words, what they're doing is they're showing you, like if you like PV and Pivnert, if you correct the P and the V for non-ideal behavior, this is how you would get the V that you would then put in. You would basically do this to it, and then put that in there. So like if you look here, if you look down here at this equation, see how I've got V above this and P above that? Like Pivnert, PV equals nRT. This is P corrected for non-ideal behavior. This is V corrected for non-ideal behavior.
Oh.
Okay.
But what is the N and B? Like what would you put there?
So the N is still number of moles. The A and the B are constants that are found on page 423. And I think usually I give you guys a copy of that. Let me, I'll show it to you and then I might have to. So like this table, for the different gases, they've got specific A's and B's that you just look on the table and then pop right into you just substitute those in for A and B.
That's nice.
Okay. So in reality, what we do, what I have you guys do with this is really just sort of a plug and chug type of thing, where I just have you put in all the variables and the stuff and then just solve for whatever part they're having you solve for. This is an example from the book where they give you, so this is Pivnert arranged for, like this is rearranged to solve for pressure. This is the van der Waals equation rearranged. And then this came from the problem. It's just everything they gave us plugged in. Okay, you've got to watch your labels. Make sure the R, make sure your pressure, sorry, not your pressure, make sure your volume is in liters so that can cancel out. Make sure you're using the right volume and R for that. The rest of this stuff comes from either that chart or whatever. So it's just really plugging it. This is all one thing down here. I didn't have enough room. There's a minus right here. It's this minus this. And then when you break it down, that's what you get. All right.